Oopsie daisy. Okay. All righty. Now we're in business, folks. I thought I figured out the license system here, but I guess I didn't. Okay. Well, on the topic of blooms and migration, we'll talk about lithium-ion migration in ceramic solid electrolytes. And one moment. It appears that this needs to be hidden. Hi. Okay. Fabulous. Fabulous. Okay. So this will span this lecture as well as Wednesday's lecture before we go into fall break. On Wednesday, we will also talk about your upcoming proposal, aka white paper, if you will, in the vernacular of grant proposals. So I'll go over the template, also expectations, the rubric, and then also I'll go over citations. If you don't already have one of your preferred citation managers, we'll spend just a little bit of time so that if you're not already there, you'll be there and your life will be easier so that you're not, just wasting your time on citation management. But really, there's free software already out there that should make your life quite seamless. And if you're already using one, they're actually translatable or portable within one to the other, as long as you have your bibliography. So we'll go through all that, and then it'll also be anonymous peer review. So I'll go through that and how we keep it anonymous, but basically, Carmen has a system where you will anonymously review each other, so that as long as you don't provide any identified information in your proposal, it should really be anonymous and constructive when folks. Yes.
Are the guidelines like that assignment like posted already, or?
The assignment has not been posted. What we're waiting on is Professor Grassman and I are trying to decide. Well, you have the due date, the week of the due date. We're just trying to balance some other schedules so that it's not all too much at once, because some of you are also in the 5532 electronic and optical materials lab, and so we just don't want to pile on. So we're making basically final decisions today, which is why I'm going to discuss it on Wednesday. But we have the template that's all ready to go.
So do you think we'll work on it during fall break?
You may, if you want, but you have quite a stretch of time before the due date. Obviously, you're not advocating for procrastination, but if you have major plans already for fall break, and if it doesn't include ability to access Wi-Fi, for researching, then obviously that is not expected. So, but you will have a very long stretch of time to research and think about the topic that you want to talk about. And then after that, we'll talk about how we're going to pair you, actually put you all in groups, because it'll be in the end a group presentation. So your individual contributions will be graded as well as your group work at the end. So, any other questions? So if you didn't get enough of crystal structures from the last, however many lectures, you're going to see much more of it today, because crystallography will determine the properties that you measure at the end of the day for ceramic solid electrolytes for lithium-ion battery applications. This slide says a lot. This is, if you want to electrify vehicles, these are the metrics that you need to hit. Right? So where are the materials got? This is a very recent paper, as you can tell, 2021. Where are we going? Where do we need to go? Well, not only do we need to think about material development, like making the material, designing the crystal structure, what material do we actually want to engineer in the cell? We then, once we get there, we still need to think about the and stable material. So this is a very small bullet point, but it's extremely important because once you design the material science aspect of your solid electrolyte to replace liquid electrolyte, you then have to engineer a stable, electrochemically stable material to get you towards the finish line. Because anything that's going to be put up against lithium metal anode is going to reduce and cause decomposition in the material. Now, what the decomposed products are can be advantageous. They can also be disadvantageous. Obviously, what you want is you want to engineer. If you know your fate is decomposition, you might as well design something that will decompose favorably for your application. Something that we think about quite a bit for, designing new materials is how scalable is it, right? Are we going to go down the path of using more precious metals or materials that are really expensive? So we need to think about scalability in terms of cost, scalability in terms of manufacturing, making the materials, and reducing the interface. The electrode-electrolyte interface is everybody's problem. It doesn't matter if you work on the electrode, cathode or anode, or the electrolyte. The interface is always going to be the most difficult engineering problem in your battery system, besides the systems problem, which is, okay, once you have one cell to work, how do you get 5,000 of them to work together well? And of course, for the other engineering gap is once you have your material, once you can scale up, right? How do you achieve long cycle life? What voltage windows are you going to operate over? How do you package your batteries so that you reduce, thermal waste, things like that? How do you reduce the thermal waste? Can you couple it with another technology like thermal electrics, where you can convert heat to electricity? Right? So there's a lot of processes that go into developing a new full cell, a full solid state battery. So all solid state, everything is solid, there's no additional water. And if you want to push the boundaries of energy capacity, you need greater than 500 watt-hours per kilogram is ridiculously high. I mean, that is like, one of those moonshot objectives. Volumetrically, 1,500 watt-hours per liter, and this costs, we're nowhere near this. You're paying probably 300, maybe a little less than that, 200, 300, depending on the car you buy, the battery that you have. But this is a really low number for where we are right now. But these are lofty goals that we all need to aim for, or else we'll never get there if we don't try. Right? But these are numbers that will make electrification of vehicles with solid state batteries, a reality. In the world of solid electrolytes, you're going to see a lot of these Arrhenius type plots. You probably have seen, them in terms of ion conductivity in, let's say, when you're studying diffusion. You probably have seen this. Conductivity is a function of inverse temperature. So this is 1/T times 1,000. That's in inverse Kelvin. If you convert inverse Kelvin to Celsius, you get this scale. So the x-axis up here is also the same as the x-axis down here. So it's easier to convert, but this is in the units of which you calculate your ingredients equation with, and this is the more human friendly units. So this is a lot. So we're going to break down how all these materials come into play, but these are basically the state-of-the-art materials right here, including lithium nitride, which if you've taken the 5532 class, we talked about how this is what you don't want. This is highly resistive, but this is highly resistive in terms of electrical conductivity. But for ionic conduction, it's not that bad. If you want to have your solid electrolyte in the middle to be electrically insulating but ionically conductive, it's not that bad. And then some of the other materials that we'll talk about are here. So Lycon, that's an amorphous material, is lithium phosphate with nitrogen in it, so nitride. It actually was worked on 10, 15 years ago, but since then, a lot of the sulfides have come into play. In fact, biophosphates have come into play. And so there's been a lot of development over the years in terms of pushing solid electrolytes so that it's competitive with liquid electrolytes. Yes, Alan.
So in terms of materials that have big value on this graph, would it be
Yes.
safe to say that obviously you're going to pick something for a specific purpose, like use, but like you would want something with the most shallow slope and the longest range, is that correct? Is it stable across more temperature?
Yeah, so correct. So you said largest range.
Right.
Yes. Higher ionic conductivity, so higher y-axis.
Right.
And the third one you mentioned is shallower slope, aka activation energy is lower. That would be the most ideal case. But as you can tell here, there's going to be, when there's a change here in your curve, right? That's a phase transformation with a different, at least a different mechanism of ion conduction. So that's something you have to worry about. And also, some of these compounds, so while here, so this is LGPS, as we call it, lithium germanium thiophosphate. It's one of the highest ion conductivity at room temperature as well. So you can see it's pretty high up on this curve or on the y-axis here. So things that are lower have lower ionic conductivity. But what this plot doesn't show you is one of the most important parameters, electrochemical stability. Right, when you want to use a cathode material that's high, like the ones we've been talking about, 3 volts versus lithium, 4 volts versus lithium, pushing it to 4.7 volts versus lithium plus. What this plot doesn't show you is how stable these compounds are at those voltages. That's where decomposition happens, and this is where most of these compounds will fail, if not actually all will fail. So that is the other part of the engineering aspect. The material science is obvious. It's basically your simple Arrhenius, diffusion concepts, but engineering something that's stable against both something really negative like lithium and something really positive like a high voltage cathode it's like, you're trying, there is no Goldilocks in that case. You have to have some additional buffer layers. Okay, so once again, similar to cathode, almost every element in the periodic table that is reasonable, earth abundant, has been looked at. So typically what happens is you look at elements that can diffuse, right? So these are the alkali earth, and then the ligands, so the anions that surround the cation typically are over here. So you've seen oxygen, we talked about nitrogen, we talked about some sulfides, which is going guessing, we talked about the halides as well, larger chalcogenide ions like selenides, and then, what's called cation forming the polyhedral skeleton. So when we talked about, like thiophosphate or just phosphate like PO4, you can also have silicates and aluminates and borates and all of that. So basically, people have investigated. What people haven't looked at, obviously, are the 3D transition metals here that you see and some of the expensive precious metals, because it's just not realistic to engineer something that has platinum in it, even if there's a light sprinkling. So unlike electrocatalysis, where you need a little bit of platinum, here that's really not the case. You need the newer scale much more so than that. So when we discuss solid electrolytes, we're going to discuss mechanisms of ion diffusion first, and then we'll go into different classes of materials that have been investigated for use in lithium-ion solid electrolytes, and it's all based on the crystallography. So it's all based on the crystal structure and how we think about engineering higher ionic conductivity by manipulating either the compound stoichiometry or the crystal structure itself by stabilizing, let's say, a high temperature phase at low temperature. So, as Alan gave you the punchline, it's going to be an Arrhenius thermally activated process for diffusion. So we'll take about 5 slides back from that comment, which is the punchline, and first think about just ions migrating in a solid. Typically, if you have a material and it's crystalline, you're going to go from one crystallographic site. So the lithium ion is going to go from one crystallographic site to another crystallographic site. right? In an ideal crystalline case. So if your ion is in this position, energetically, it's favorable, right? You have a stable compound, the energy is low, but for the ion to then migrate to another crystallographic site, it has to overcome some sort of energy barrier. So that was the activation energy that Alan referred to, right? You have to overcome this energy barrier. Well, what is this energy barrier? If you think about, if you're just agnostic about the crystallography, and you just think about, I am an atom, I'm an ion, and I just want to get somewhere else spatially. Well, you could be in a glass, you could be in a crystalline material, you can be wherever, but the energy that's going to cost you is this Gibbs free energy of migration, labeled as GM. So this energy is delta GM. Now, what's convoluted in this delta GM is also the formation energy for you to jump from one site to another site, as well as the entropy that goes with it, right? So once you break the bond from your nearest neighbor to go to another site and reform bonds over there, that's your enthalpic part. And then as we revisit again, Gibbs free energy, there's an entropic component. So you have a delta SM component all in here. But for now, fundamentally, you overcome some energy at a certain temperature. There's KBT, Boltzmann constant in here. So the energy of migration really is just, you have to get over the saddle and into another energetically favorable position. And that probability is just defined as this P equals e to the negative delta GM over KBT. Right. So if you increase temperature, you can start thinking about, a statistical mechanics sense where you're going to increase your frequency, your hopping rate, the number of times you track. Okay, so simplistically, this is it. This is all an ion is trying to do, crystalline or glassy or what have you. It's just going to have to overcome some energy. In more detail, what really happens is if you have a crystallographic site, right, the ions are always going to be vibrating. This we know, right? Ions are never standing still. They're always vibrating. And that vibrational frequency increases as a function of temperature. And a typical rate is 10 to the 13 hertz or times per second. Okay. Interestingly, this is also the rate if you're looking at like Monte Carlo, ions. If you're inducing some sort of phase transformation, ions move. That's also the same rate as the catalysis. The absorption rates onto a surface before you use the catalytic process. That's also actually the same rate, or order of magnitude, anyway, 10 to 13, basically. Okay, so then if you apply some sort of bias, right now you're going to say, okay, I'm going to apply, I'm going to make myself, and now I'm going to actually try to get my ions to move from one, through the electrolyte, right? And ions are going to move from cathode to anode or anode to cathode. There's going to be some bias potential, right? So now there's going to be some net velocity. Your ions are now in motion, out of equilibrium. So that net velocity is V sub m in the direction of the applied field. And then what happens is basically you still have the energetic term that you have to overcome. And the amount of time it tries is all dependent now on the material. This is all subsumed in this prefactor here. But the prefactor, well, what is the prefactor? Okay, well, how many times is it going to jump, right? Your atom frequency. The charge on the charge number of ions. So is it lithium 1+? Is it sodium 1+? Is it magnesium 2+? That gets subsumed in your prefactor as well. KBT, temperature that you're at. The jump distance, how far does that jump? So now this goes back to the crystal structure of your material. In any material, you have a crystal lattice. You know the lattice parameters, you know A, B, C, you know the angle, alpha, beta, gamma, right? So if it's cubic, it's all the same distance, all your last parameters are the same. So this takes into account your crystal structure. So if you say, okay, well, I have whatever, sodium chloride. Is sodium going to jump from one sodium ion to another? From one sodium site to another sodium site, you know what that distance is because you know the lattice parameters of sodium chloride. So this is all calculatable. You make a data table. That's pretty convenient. So that's it. That's your net velocity. That's of the ion. And then you take all that and you revisit, okay, well, how do I get from that to ionic conductivity? Well, as you know, ionic conductivity is just your mobility times the charge times your carrier density. So hopefully photovoltaics is coming, the simple equation of conductivity is coming back. So you replace all these values in, you still have your energetic term. You now break the Gibbs-free energy into the enthalpic as well as your entropic term. You subsume everything, you call it sigma naught, as we all like to do. You say, okay, these are all terms I can tabulate. Boom, I'll call that sigma naught. So then you get in and you say, if the entropic term is minimal, which for the purposes of this course, we're going to assume it is, then you basically get left over the enthalpic term, which is your activation energy. That's what we call the activation energy. So now this resembles something that you probably have all seen, which is if you take the log of both sides, you get ln of ion conductivity. So you can see why this is in log form as a function of 1 over t, whereas your slope is negative dA over kBt. Okay. And then this is all like just stuff we can put in, the prefactors and stuff that you can tabulate and plug in. Okay. So this is generalizable to any crystal structure. Okay. So in the end, you get a plot that looks like this, and you see, okay, well, this is what we've been talking about: 1 molar LiPF6 and ECDMC. What we have to beat is basically 10 millisiemens per centimeter. That is the number we have to beat in terms of designing a solid electrolyte that has comparable ionic conductivity at room temperature to that of liquid electrolyte. Okay, so 10 millisiemens per centimeter. More like 5 is good enough, but 10 will surpass it. Okay, so then you have some other compounds here as an example. So what people had worked on before, Lycon, so still not as high, but it works, so that's pretty stable. Then you have these compounds called garnet, thiolisicons, some lithium lanthanum titanate, and we'll go into great detail each one of these materials and their crystal structure and why they have high ion conductivity and why they're competitive and why people are engineering all these stoichiometries that you see here. But really all it comes down to is if you know the crystal structure, you can calculate the ion conductivity at each temperature. What you want to do is you want to increase ion conductivity at room temperature because that's where most of us live. Although if you have a high temperature application, then you can think about materials that are more stable at high temperature or low temperature application. But for the most part, if you're thinking about electrifying vehicles, you're thinking about room temperature more or less applications. Even if you're in like a very hot or cold environment, you deviate mostly from room temperature. So the rules of the game for designing fast ion transport in the material. You want high dimensionality of the conduction pathway. What does that mean? That means you want a crystal structure that can enable lithium ion migration in all 3 dimensions. Right? If you've heard of like 2D materials, all the quantum materials that are now 2D, that's really good for those applications. But in ion connectivity, you want your fast ion migration in all 3 dimensions. You don't necessarily want fast ion diffusion in 1D, because then you're gonna have to align your crystal structure so that ion transport that's fast is all from, in one direction from the cathode to anode. And that's extremely difficult to do. Manufacturing wise, if you have a polycrystalline material, that's easier to work with than like a single crystal, which is also quite difficult to grow. Okay. You want high carrier density, which you can improve by aliovalent substitution. All that means is you substitute one of the sites with a different charge. We talk about aliovalent substitution in great detail. You want low enthalpy of migration. That seems like an obvious thing. You want some low energy with the bond that you're breaking to not be that ionic. You don't want, the anions around lithium to be so strongly bonded that it won't actually break and then enable lithium ions to migrate. Yes, Al?
A different charge is still the same, like, so positive to like +1 to +2, not +1 to -1.
Correct. Yes, you did. Say yes.
Your sweet spot and bonding energy, like how strong bonding to be, like you can't have like really big hydrogen bond or anything like that.
Yeah. Oh, you mean like secondary
Yeah.
forces? Correct. Yeah. So you still want it to be a covalent bond so that it's strong enough that your material is still,
Together.
yeah. But at the same time, you don't want it to be too strong. So yes, there's a sweet spot in the middle there. Now, there's always an asterisk with every answer, right? The nuanced answer is, well, if you think about like van der Waals, right? Secondary forces, right? Van der Waals forces, that's a weak bond. But if you had really fast ion conduction, could you, in one direction, or in 2 directions, like in the plane for like a van der Waals type material, could you align it so that, the fast ion conduction is in the direction that you want in between your 2 electrodes? The answer is always yes. You can always do that, but it gets tricky because then you lose that 3rd dimension. So then you change your entire manufacturing line, so that you can do that. So if you had like, obviously, if you have a material that just outperforms all others, like, consistently, then potentially you could redesign manufacturing. But the low cost, path of least resistance is a material that can conduct in all directions. Yes. Let's see, right. So low enthalpy migration, that depends on lattice polarizability. Polarizability, we'll talk about that term. Path of migration, lattice strain, geometry of conduction pathway. So all this ties into the crystal structure of the material, as well as high entropy migration, which we will not discuss, but that is something, to think about. We'll talk about the first 3 points. Okay, so here is a compilation of all the compounds. Okay, the majority of the compounds of interest, not all the compounds, right? These are basically the leading materials for, it's the same plot, but in an easier to see version. So here's ion conductivity. X-axis doesn't really mean anything other than, classes of families. So if you had to pick an ion conductor, a class of families to work on, and your entire goal is high ion conductivity, which would you pick?
Would you repeat the question? You kind of fell a little there.
If you had to pick one class of family, and your entire goal is high ion conductivity, which one of these classes of materials would you pick?
See the one in the middle, that short little purple one?
Lithium, silicon, phosphate, sulfur.
Yeah. Because,
This one?
yes, because
Okay.
that one is guaranteed. If it works, it seems to exist at the high conductivities. There's very little range to that.
Right. Okay, so there's that. So there is this. Are there any other concerns? Okay, now that you've satisfied, that one criterion, are there other concerns looking at this class of all these compounds?
Well, you didn't say that. You asked high conductivity. That was a single criterion, so I answered based on the single criterion.
Yes, you did answer my question. My follow-up question is, are there any other concerns when you look at a plot like this? a general view.
How wide the range is for some of them?
How wide the range is for some of them. Okay, so yeah, this is pretty large, this is pretty small, this is pretty large.
Is the bar, so there's a thick bar at the top and the bottom, is the bar in the middle, the statistical average?
Oh, yeah, sorry, I didn't actually specify. These these three bars are just different stoichiometries. So if you replace, if you decrease the germanium content, say, for example, or that sort of thing, then it would end up somewhere here. So you're just changing the composition within these two end numbers.
So the
Okay.
one on the far right, also borate family is
Yeah.
the absolute largest? Or
Ah.
is it the highest conductivity?
Yes, for sodium ion conduction. What do you think is an issue if you work with hydrogen?
High reactivity?
Yeah, so borates, the boryl hydrides can involve hydrogen. So safety is a concern. This review paper does put sodium ions in the same chart with lithium ions. So yes. Yeah, so generally it is exactly what you intuitively think when you see a plot like this and haven't read this, very long review paper. It is just that. It's number one, what's highest ion conductivity? Number two, are there safety concerns that I should be thinking about? Number three, why is there such a spread for some of these compounds, but a tighter range for some of the other compounds, right? So it all has to do with, if you're changing the stoichiometry, then it has to do with that. Like, why are some classes of family much more sensitive to changes in composition and the performance, like the ion conductivity? And why is it that some of them, not so much? Right? And it all has to do with the crystal structure and all the previous parameters I talked about, the lattice strain, the path of migration. Some compounds, when ions migrate, those things don't matter as much, or they don't affect the ion migration as much. But other compounds, you can see, have a wide variation, especially when you're working with solid solutions. So the point is, it's the crystal structure, but also it's what happens to your crystal structure as your ion moves through your material. It's the disorder. And it's not always like, oh, if you bring more disordered materials, like atomically disordered, you have, you sprinkle in some few more elements, say, or different cation set. It's not always that disorder will guarantee higher ion conductivity. Sometimes, as your ion is moving, the dynamical process affects the disorder, creates disorder as well. So it's a little bit like chicken and egg. And the way you study that is you do, you cycle your battery and you look at the crystal structure as the ions are migrating to study that. Right. Okay, here's another wonderful plot. I do love these pretty summary plots. So that was ion conductivity. Now we look at the slope. This is activation energy for the same classes of materials. We'll focus on the lithium ions over here on the left. So you can see the activation energy is quite high. You want now lower activation energy, right? So here we're looking at this LGPS family of compounds. But you also see, well, if I didn't want to work with sulfides because, like H2S can evolve, that's a toxic gas. Although, if you've ever smelled rotten eggs, you just smell H2S and, you haven't died from that other than, an unpleasant experience. And that's because your nose is very sensitive to parts per million concentration of H2S. So H2S is toxic. Obviously, you're in a room with H2S gas from a tank. That is very toxic. But if you're just smelling H2S from like rotten eggs or something like that, that's not so toxic. But that's a concern for any one of these compounds that have sulfides in them. Is as soon as they see moisture, as soon as you have any exposure to even small amounts of H2O, like in moisture, H2O in the air, that kind of thing, you're going to start evolving H2S. So how much H2S can you safely work with, right? When making these compounds is a safety issue. But So far it's looking like high ionic connectivity, low activation energy. Clearly this LGPS family is winning based on those metrics. Once again, I didn't tell you if it's electrochemically stable, but the way I keep teasing it, you probably know the answer. It's not that electrochemically stable, right? So you have to engineer a buffer layer so that it is stable. More equations. So how do you get diffusion coefficient out from ionic connectivity? Well, statistically, if you just think about a random walk, if your ion is just hopping, like there's no constraints, it's just moving wherever it wants. Then once again, there's some energy barrier that it just has to overcome. So that's just statistics, right? There's nothing so magical. We haven't talked about crystal structure. We haven't talked about classes of family. There's an ion and it wants to move. It's just going to be what's called a random walk. Okay, great. So your diffusion coefficient is going to be based on energy barrier that has to overcome. And so the long-range macroscopic ion connectivity that you measure will then be just a consequence of the microscopic, what's happening, at the atomic scale. Okay. And you can relate the two. You can relate ion connectivity and your diffusion coefficient. Through that relationship, and it is called the Nernst-Einstein equation, where you can relate the measured ion connectivity, you can calculate out the diffusion coefficient in your system. Okay, so that's that. But is that really the case? The answer is no. What happens is you measure what's called a tracer diffusion coefficient, and that's usually smaller than this d of r, right? It's really not your system, a realistic material is not going to experience a random walk. Your lithium ion isn't going to, just migrate in whichever diffusion, or sorry, it's not going to diffuse in whichever direction. There's going to be what's called correlated motion. And what that means is, right, based on the crystal structure, the ion is going to have a preferred pathway. It's going to look at energetically its neighbors. It's going to look at its second nearest neighbor, and it knows which way which way is the path of least resistance. Which way is going to have the lowest energy barrier, and that is the path it's going to go to. And then once it makes that hop, let's say it goes into another crystallographic site, or it goes into an interstitial site, then that changes. Now it's in a new environment, and if it's in an interstitial site, the energy landscape around that site will dictate its next move. Okay. So it's quite a dynamical process. So not just a random walk. So that correlation will show you for a material what's called a Haven ratio. So that's basically the discrepancy between the microscopic ionic diffusion and what you actually measure, macroscopically. And that's typically this scalar F is typically less than 1. But it all goes back to your crystal structure and the correlated motions in your crystal structure. So what exactly happens around, in terms of the energy landscape around the lithium ion, and how do you increase ionic connectivity? Well, there's a concept called polyhedral connectivity, and that tells you if an ion has to move through, let's say, a tetrahedral face going into another tetrahedron, or an octahedral side, in the center of the octahedron, so 8-sided polyhedron, and then migrates to another octahedron and then into a tetrahedron, that affects what's called, the bottlenecks that it has, So here's an example where if it moves through a tetrahedral site, the energy barrier is about 0.2 eV relative to, let's say, going from this blue and then migrating along this green path. So you can actually predict and calculate ab initio. So you go into the computer, you set up your crystal structure, and then you can do calculations to find out what is a preferred path of migration, just based on energy. And you can calculate all of this. You can say, if I put my ion here, right, that's a favorable site because it's far away from the anion. So here is a lithium ion. Let's say these are oxides. The orange can also be sulfides. It doesn't matter. But here is a crystallograph, energetically favorable site. As soon as you start moving it away, you can literally just set up your program, put the ion, a little bit away from center, and then you calculate the energy at each one of these data points. So you perform different calculations. If you're in Professor Wendell's class, you probably would do this. You can then map out the energy landscape. So you perform these calculations, you map out the energy landscape, and then you do the same thing. So you can see here that it's just a linear extrapolation. You just guess. Well, I mean, would the ion kind of deviate like this? Yeah, maybe. But as a first approximation, you say, I want to go from A to B in a linear fashion. How much energy is that going to cost me? And you can make that calculation.
Even if it did deviate, would the energy be the same since it doesn't take a longer path to a lower energy path?
So it depends on how it deviates. Like for whatever reason, let's say you have a point defect here. Let's say you have a vacancy for whatever reason, your synthesis, you lost some material, but the vacancy concentration is low enough that you still have a stable crystal structure and you have some powder in front of you. That might, induce a deviation. Let's say, if this is a plus charge, this is negative, and this is neutral because vacancy, it could move towards there just because there's more room to breathe, it kind of relaxes away. That could happen. So you would probably see a deviation, maybe a lowering of this energy barrier. So you would see that if you introduce things like point defects, like a higher vacancy concentration. But how much of a depression in terms of the activation energy depends on your vacancy concentration, and also it depends on the correlated motion. Like how significant is this nearest neighbor? The lithium vacancy bond energy versus the lithium and an anion bond energy. All of that is taken into account, and sometimes you don't know a priori, as in you make one lithium site jump. If there's another lithium ion site, so let's say this is for one ion migration, but let's say you have two ions close to each other for whatever reason, do they move correlatedly, or do they try to, go, they would go in opposite direction, but how would they move? That depends on your material, and sometimes you don't know until you do the calculation. But in terms of general, just a basic fundamental concept, the polyhedral connectivity does matter if your lithium ion is sitting in an octahedral site or a tetrahedral site. It gives you an idea of the energy barrier that it's going to have to overcome. Now, how do you know you're sitting in an octahedral site or a tetrahedral site? Well, you open up the crystal structure and you look at it, you look at the symmetry, and then you know. Okay. There's another way to engineer higher ion conductivity, and that is just to move things out of the way for the ion. So it's called widening the diffusion pathway. So if you see here, energy barrier is much higher than that of this system, where the pathway, the bottleneck is you open it so that your lithium ion doesn't have as much energy barrier to go through. So that's called engineering the bottleneck size. So you say, okay, well, how do I do that? Based on this drawing, you could see, well, I just changed the anion. So I go from oxides to sulfides and move down in the periodic table. Sometimes it is as simple as that. That's literally it. There isn't much to say about that. So just changing your ionic radii. And then there's also something what's called dynamical effects from lattice softening. And you could also do that by going from oxides to sulfide. The bond now, a lithium oxygen bond versus a lithium sulfur bond, you soften the lattice. So the energy now will also increase. Yes,
So
Dagny.
that line is bigger, and I
Mhm.
has a lower energy, but
The effective nuclear charge is lower because you're going from an oxide to a sulfide. Yeah, so the sulfide anion is larger. Yes, S2 minus is larger than O2 minus. But you're also just, the larger anion, that means your sulfide bond distance is longer. The oxygen as well. So basically, you're just enlarging your lattice. Your
you're
crystal-
learning a lot more here.
Ah, yes.
Like, because the atom is bigger, but it's not. There's a lot of by the way. Like, by the factor.
Yes, in isolation, yes. Basically, you just move everything out of the way. Everything being the anion, you just move them farther apart so that the bottleneck is bigger. So the path of migration is bigger for your lithium ions to go through. So that means as your ions moving through this particular pathway, it also is the bonds are weakened, so it can break, form, reform. Yes, I should say. Okay. Now we get into crystal structure and lots of crystal structures so that we can understand how each class of family is different from each other. We start off with the lithium, what's called lithium garnet. The garnet, this is the crystal structure for lithium garnet. It is one of the most studied lithium ion solid electrolytes out there. It's also the most, I would say, mature because it's also air stable, more or less, as in more than the sulfide, but not that stable because once it sees moisture, it will actually decompose to other compounds, by the way. So it actually has to be stored in an argon environment and actually can't really, it's not that stable. But it is more stable. It's also stable against lithium now. So you put what's called LLZO, lithium 7, lithium 3, zirconium 2, oxygen 12. If you put this compound up against lithium metal, what's most attractive about this compound is that it is stable against lithium reduction. It doesn't readily decompose other compounds. But let's look at the ion conductivity as a function at room temperature. You can see that it's 0.3 millisieverts per centimeter. So it's still not as high as 1 molar LiP of 6 and ethylene carbonate dimethyl carbonate 3 to 7 by volume, but it's getting up there, right? So it has this is what's called high ion conductivity, but it's not so high that we can readily replace liquid electrolyte with this compound alone. It's stable, but if you try to charge and discharge too fast, this ceramic material, right, it's still porous unless you densify it. So that's what people try to do. So the lithium filament will actually still grow and your battery will still eventually short. And why I call it lithium filament as opposed to the lithium dendrite is because dendritic formation is a function of the solidification process, which is a liquid to solid process. Here, all of the materials are solid. Okay. So you have lithium filament growth. You don't necessarily have dendritic growth, but it's a technical definition of what a dendrite is. So that's what people do. They'll start off with this material. Here is, you could see some voids. And in this particular study, they looked at LLZO, although they put in a little bit of tantalum and niobium as well to increase ion conductivity. So you can see at high, so this is HP, so this is high pressure. They also sinter at a high temperature to densify the material. So you can see the voids have decreased, which is a good thing because then there's no pathway for lithium filament, or there are fewer pathways, fewer low energy pathways for lithium filament to grow, which is really which is desirable. The cation disorder. So when you start substituting the zirconium side with some tantalum, you induce what's called cationic disorder, and that also increases your ion conductivity. Okay. So let me so I'm putting on here the all these crystal structures that you see here so that you can go around. So you can go into Citrix and you have access to Vesta. You can also download Vesta for free. And I've already saved these files. If you want to download from whichever database you want to download from, you can download the crystallographic information file. You can also just download the Vesta files that I'll upload to Carmen, and then you can just look around. But you could see here, let's show the lithium sites because that's of interest. So you can see there's a lot of lithium sites, and they are these, they're partially occupied. That means sometimes they're here, sometimes they're also here. You can see the cage, so the polyanionic framework. So these are all the lanthanum. So the purple is lanthanum. The other dark purple is the zirconium. So this is the ZR06 octahedra. So if you count, there's 4 faces here, 4 faces here. That makes an octahedron because it's 8. And you can see now that let me take away some of the labels. You could see, let me just do one of them. So you can see how the lithium ions are coordinated. So you can see in the green, those are tetrahedra. So that means there's 4. Lithium is coordinated to 4. So those bonds have to break for it to then migrate to another site. Okay. And so people have studied this structure quite a bit because it's stable against lithium metal. And if you use lithium metal anode, then you can increase your energy density significantly, which is a highly desired objective in the electrification of vehicles. Okay, so we'll stop here. We'll go through the other compounds on Wednesday, in addition to talking about your proposal.
Sorry, do you use this tool a lot in the professional environment?
Yes, the crystallographic community uses this a lot. There's also the paid for version. MSE has a site license crystal maker. I believe it's already on Citrix, so you can probably just go through that. Different software, you do the same thing. This one happens.
Awesome once it does work on Citrix.
Okay, yeah, there you go. So the solid state chemists use this. There are other visualization tools, whichever one you're comfortable with. Vesta should be able to port to Crystal Maker, no problem. Yeah. Alrighty. See you Wednesday. Yes.